There you go.
Oh, that's okay. Good evening, everybody.
Hi.
Thanks for coming out for Science on Tap. Please tell your friends, your colleagues, if everybody brings a buddy, we need to fill this place up.
Come for the tap, stay for the science.
No, come for the science and enjoy. Yeah. Science on Tap is a collaborative effort between MOSH, the Museum of Science and History, University of North Florida, and Jacksonville University, and wonderful Lemon Street Brewing for hosting us. So let's thank them for the great beer. It is our pleasure to have Dr. Brian Lane of the University of North Florida present tonight. He got his undergrad degree from Jacksonville University, and then he went to the University of Florida for his PhD. He used to work at JU, and now he is currently at UNF. So without further ado, Dr. Brian Lane is going to talk all about science education. So, go Brian.
Thank you, Natasha. It is so wonderful to see so many of my still friends, former colleagues here. I want to talk to you tonight about, this is in my way, there we go. I want to talk to you tonight about learning attitudes. I will be defining that shortly. Just know that that's a vocabulary term for you. I'm branding that as the next big puzzle in science education, and I hope within the first couple minutes to persuade you it is a puzzle and it is a thing we need to talk about and we need to start working around. The main point here is that we must develop students' attitudes along with their knowledge. That we don't just want to give them information, but actually develop their attitudes, their feelings, their beliefs toward that knowledge and towards how they get that knowledge. I do want to acknowledge my collaborators who I do not take a large amount of cost, but my 3 undergraduate students and my colleague in the Department of Physics who have worked on this for the last year and a half now. I have a QR code to our paper there, but I've learned that people don't scan on the title slide, they scan on the conclusion slide after you've shown them that they should be interested in the paper. So I'm going to have that up again at the end. Before we get started with the outline slide, I want to do a pop quiz. Can anybody tell me what this graph is?
COVID.
Yeah.
Coronavirus.
Coronavirus is this, okay, this, we have an answer of coronavirus deaths. Anybody want to give another guess?
S&P 500.
S&P 500? I'm going to talk about that in a second. This is a very close answer. This is a very close answer. Because about this region, I'm not claiming to be exact on this, but about this region, yes, is deaths due to COVID. And you notice at the end of that it starts to tail off, it starts to taper down, because we knew at that point that lockdowns, masking, and distancing were working. We were beating this thing, we were going to win. And then we entered this region. And these are the people who died, yes, from COVID, but at the hands of science denial. Because it was at this point that our leaders decided, yes, this science stuff is working, we are definitely winning, we are definitely going to save lives with these measures, but economy. And I put it to you here, when you put business in charge of the sciences, this is what happens. Okay, so now that I've got your attention, right, I want to talk about what is a learning attitude and what does it have to do with the horrific situation we've been through over the last 18 months. How do we assess a learning attitude? Because I'm a physics education researcher. If I'm going to talk about a thing, I better be able to assess it, right? And so I'll talk to you about my favorite tool, my absolute favorite thing to do in physics education, which is give this one survey called the CLAS. Then I'll go over some bad news for the science and math educators in the room. We are bad at this. But then I'll have some interesting news where we might not be as bad as we think we are. This is where it's going to get a little muddy. And then I'll talk for a minute at the end about what we might do differently. So for the science educators in the room, for the science and math educators in the room, sorry, I'm trying not to lump math with science, I know we're supposed to call them separate. But for the science and math educators in the room, I hope this is some useful tips and tricks. For the everyday folks in the room, I hope this is still useful in terms of how we approach science as a society, how we talk about it to our neighbors, etc. So when I use the term learning attitude, what I'm referring to is an attitude or belief that shapes or is shaped by the student's experience in the classroom. So you can broadly think of this in terms of 3 categories. We're going to get a little more finely grained in a couple slides, but the 3 big categories are: what is the source of scientific knowledge? Is scientific knowledge something that is handed down to me by the expert, or is it something I can go and learn about myself? Right? Or there's relevance. Do I think that science is very relevant to me and has lots of applications for my life? Or do I just think it's something that old white dudes do in a lab over there and then they die? And then there's an element of confidence to this too. Do I feel like science is something that I am capable of approaching and doing? We're just talking about that in a math context, that the first learning objective in the non-majors math course is, I want you to believe that you can do mathematics, right? So these learning attitudes fall on a spectrum of novice-like to expert-like. So I've got some example statements there. You can probably imagine the extreme examples of this between a novice saying, well, science is something that the expert has to hand to me because I can't do it myself, versus anybody can learn science because everyone is capable of it if they try hard enough, right? So our students fall somewhere on that spectrum. I've never seen a student that was 100% novice. I've also never seen a student that was 100% expert, but even I'm probably not 100% on the expert scale. I probably have some vestigial learning attitudes where I'm still operating out of a novice mindset. But what we would like to see would be for students to go from novice to expert, at least a little bit, right? Keep that in mind, that's our goal. And the thing I want to do to tie this to COVID is that these learning attitudes might represent ideological commitments. Some of it's just plain old, I like it or I don't like it, but some of it gets very esoteric and heady in these students' minds about their commitments that science may align with or may anti-align with, at least as far as they experience. So how do we assess this? Well, my favorite tool to assess learning attitudes, there's a few options out there, but my favorite one is the Colorado Learning Attitudes About Science survey. They originally wanted to design the survey about science in general, but then they discovered that was too mushy. But if you make it a specific subject, you can actually get some very interesting data on this. So there is a physics, a biology, and a chemistry version of the survey that read very similarly. It just trades out physics for chemistry and biology, etc. So the way the survey works, you give this to the student at the beginning of the semester and the end of the semester so that you can capture some sort of change. And you give them these 40 some odd statements about science. There's no right or wrong answers, it's literally all opinions. And you tell them this on the first day, and you say, this is a survey about your opinions about physics. There are no wrong answers. This doesn't affect your grade, this is just, I want to learn what you think. And it turns out if you ask students what they think, they're pretty willing to tell you. So the way it works is some of these statements are designed that an expert's going to agree and a novice is going to disagree, and some of them are designed the opposite. That's just part of survey design. You don't want them Christmas treeing it, or you want to be able to tell if they're Christmas treeing it. So like you can see there, you've got some in purple, some in green. I've got those color-coded to expert and novice like. And what you do is you resolve the score onto how many statements did a student give an expert-like response to, and how many did they give a novice-like response to. Just a caveat for the statisticians in the room, neutral does not count toward either. So you actually end up with 3 scores. You end up with a % favorable, a % unfavorable, and a % neutral, and those all 3 add up to 100%. We're only going to focus on the % favorable because there's not a whole lot of independence to them. If % favorable goes up, % unfavorable usually goes down. So we're just going to focus on the expert-like score, the novice-like score. It just goes the opposite. And so the goal, obviously, we want the favorable score to go up. We want the students to come in at the beginning of the semester and to leave at the end of the semester with a higher score than when they came in with, right? Basic testing ideal here. And then, of course, there's the bad news. So if you look at this graph here, we have the pre-scores in blue and the post-scores in orange. So I invite you, what do you notice about this graph?
It goes down.
It goes down, right? So a little bit of technical information, those vertical lines there, those are the standard error bars. So if you don't have those vertical bars overlapping, you have a statistically significant change. If they do overlap, you can kind of tell if there's a change, but it's not statistically significant. They're not different enough to count. And if you look at the blue, the pre, going to the orange post, it's pretty much bad news across the board. What you're looking at here on the very left is the survey overall, so that's all the statements on the survey. And then the rest are these categories, so you can bend these into different categories, kind of like what we were talking about earlier. They almost got a good change in conceptual understanding. It's not statistically significant, but everything else is a decline. And unfortunately, this is what we see across the board. This is from the initial CLAS paper at University of Colorado Boulder in 2006. And it's been pretty much the same story over the last 15 years, is that we get all these declines. Even when the students show that they learned something. So if you give them an actual pre-post test of what they know, their knowledge goes up, but their attitudes go down. So they are learning lots of science, but they feel worse about it, which is scary, right? You can see an increase if you make it an explicit focus of your course, but you're doing a major redesign at that point, down to the level of I am jettisoning content in order to improve attitudes, which you can certainly choose to do. I've done that. I have seen increases on this, but it takes a lot of work. This is a meta-study from, gosh, 6 years ago now. It's been a while since this one came out, but this is 25 different CLAS studies. So each one of those bars is a pre-post shift. So it's one class that took this survey. If the bar goes to the right, it means it's an improvement. If it went to the left, it means it was a decline. And what you can see, maybe you can see, I didn't make the font big enough because you never know where you're going to be presenting. But in the top left there, you've got traditional courses, both lecture-based and engaged learning, that show declines. My beloved engaged learning clicker questions are not helping students feel better. It turns out the classes that do the best are the ones that give explicit focus on model building. So if you focus on the actual construction of scientific knowledge from evidence to models, that tends to develop better attitudes. The JU folks can take this home if they want. The small courses do a little bit better than the large courses, but not by much. It's still mixed. It turns out the group that does the absolute best is the physics courses for elementary education majors. So if you throw in enough toys, people like their science. So yes, the bad news is that we tend to see these declines, right? If you put in a lot of effort, you can get some improvement, but typically you see a decline. But there's an asterisk on this, because my group has shown that there's a little bit more going on here than meets the eye. So this is some data we've got at UNF over the last year and a half, where we've given the survey at the beginning and the end. And so you go from pre to post now is blue to gold. Sorry, I could not get all the colors to coordinate, just don't hold the slides next to each other. But if you go from blue to gold, we get a little bit of improvement. We're doing okay with our 100-size student classes. We're doing okay, right? But we gave the survey an additional 2 times because we wanted to find out not just how the survey changed, but how did they think their attitudes changed? Because this is a self-reported survey, right? There's nothing really objective about this. We're kind of relying on the students to evaluate themselves here. So we wanted to get an idea of how do they think they changed. So we gave the survey an additional 2 times. If you look in the lower left here, it kind of gives you an overview of how we did this. And kudos to Ramesh for making that wonderful graphic for us a couple years ago. So the pre and post, that's the traditional. That's giving it at the beginning and end of the semester about the students' current attitudes, right? So how would you respond to this survey now? At the beginning of the semester, we asked them to complete it a second time to tell us what they expected to be at the end of the semester. So where do you think you'll be? And if you look going from blue to red, that's pre to expected, they expected to learn a lot. They thought that their attitudes were going to change, right? This is really interesting because it's like they know that they need to be somewhere else. They know that there's a more mature way of thinking about science, but they know they're not there yet, but they want to be there, right? So they think they're going to be more interested. They think they're going to be more confident. They think they're going to be better problem solvers, right? Then at the end of the semester, we asked them to do it twice. You can probably guess what this is going to be. We asked them, how do you feel about the statement now? And how do you remember feeling about it at the beginning of the semester? And so this is the retro to post. This is going from the green to the yellow. And they think they changed by a lot. And in fact, if you look at that shift, pre to expected and retro to post, it's about 10 to 20% each. So they think they're going to gain about 10 to 20%. And then they thought they gained 10 to 20%. But the floor shifts from under them so that it's a net zero. It's wild. Like it almost looks like the data is rigged there just to prove a point. It's not, I promise. And the interesting thing is, this is across 7 different class sections with 7 different instructors. And oh, by the way, we saw this exact same trend when we did the study at JU. So there's two different institutions, about a dozen different instructors, a whole lot of different course contexts and methodologies. They all seem to show this trend. This is actually not new. This is something called response shift bias. The idea is that the students are using different criteria to evaluate themselves. So let me give you an example of this. CLAS question 28, the students rate their level of agreement to disagreement on this. learning physics changes my ideas about how the world works. Right? You would like to see them go from disagreeing to agreeing. But the thing is, their ideas about what that statement means changes. So like when they see the world there, my concept of the world is very different at the end of a physics class compared to the beginning of one, or at the end of a biology class, at the end of a chemistry class. That definition of world is different. And so the pre to post, as wonderful as it is, and we want to keep using the CLAS, we're not advocating getting rid of it, it's conflating this idea of what is the survey asking about and how do I understand what the survey is asking about. Whereas the pre-expected retro post, this 4-pass treatment, however complicated the graph may look, I'm sorry, it's teasing that out a little bit better because we're getting a better idea of how their standards are changing. So we wanted more information on this. So I had seen this at JU, I came over to UNF, and I said, all right, I want to get deeper into this. Rather than just giving the survey, I want to find out why their answers are different. So we added a reflection question. We said, why did you give the same answer, or why did you give a different answer? Now, we couldn't do this for the entire survey, because that would be, we're already doubling the 41 question survey, so now we would be tripling it. So we just gave it to 4 statements. So we picked one of the categories. So we're within the same little corner of the survey, and at the end of the day, we got way more data than we thought we would, so we were still analyzing it. So we're going to talk about one statement tonight. That question 28 we talked about on last slide. And we've spent the last 6 months tagging this data. Basically, tagging, what you're doing is you're looking for themes in the data. You're saying, oh, this student mentioned getting better at math, and this student mentioned getting better at math. Let's make a theme about getting better at math. Right? And we just keep iterating on this until we get better at it. We recently found a trick. We might be able to use some machine learning software to auto-categorize this stuff for us. So we are learning machine learning. Finally, I have an excuse to do that. But we came up with some pretty good categories here. These are the themes we found in our student free responses. So again, this is asking them, why did you give the same or different answer on the 2 times that you did this survey, right? And so on the left there, we've got the themes that we came up with. On the far right, we've got the percent frequency that happened with in the pre-expected survey, and then again with the retro post. And there's a couple of interesting changes I want to highlight with this. There's a whole lot to unpack here. I'm just going to focus on 2 items. The first item I want to focus on is on this comparison feature here. This is where the students made some sort of comparison between either 2 ideas or 2 events or 2 classes. They said, I learned this in math, but then I learned this in physics. And so they're making some sort of comparison. The frequency with which they did that basically tripled. So they felt much more equipped at the end of the semester to make some specific comparisons in their lives and their thinking and whatever. In contrast, we looked at the worldview tag that we came up with. This is any statement that references their perception of the world or how they interact with it, or any absolute statements. So things like physics is all around us. Okay, that's wonderful. I'm glad you think that, but can you tell me why you think that, or can you give me an example of that? Well, physics is all around us. It's a nice statement, but it's very broad brush strokes, right? It's almost dogmatic sounding. That went from 63% of responses to 33%. So basically cut in half. So the interesting thing is, after a semester of instruction, they're relying less and less on absolute declarative, this is the way it is statements. And they're able to make more detailed comparisons about what they're learning and about what they're experiencing. So I take that as a sign they are learning something. They're becoming better equipped to evaluate their own learning experience. And that maybe there is something to this, they perceive themselves to have jumped this much. Now, of course, it's still a complicated mess, right? Because, if they think they've learned a lot, but they actually haven't, that's not great for society, right? But at the same time, if they are coming out, at this level, but they had a good experience in the class, that's something I need to capitalize on, right? And so it's complicated. It's incredibly complicated. So what can we as educators do? This is my rallying cry for the science and math educators in the room. The first thing we need to do, we absolutely need to integrate attitude development into our outcomes, into our assessments, into our assignments, into how we teach the course, possibly even more so than content. I teach less every year. Because the more semesters I teach, the more I realize, you know what, the students don't really need this section, or they don't need this problem, or they don't need this chapter, or they don't need this lab. What they need is a good experience with doing science, with being science people. And because if I can do that, they can go and learn all that extra stuff. But if they learn a bunch of stuff now but don't feel good about it, their attitude is not going to fix itself later, right? We need to use this data to motivate engaged learning among our colleagues. That yes, if we go into these classes and we make this an explicit goal and we interact with the students and we make our classes interactive, they're going to show better attitude improvement. We also need, honestly, to confront our administrators about modeling constructive attitudes towards science. Because if the students see their celebrity university president slashing science programs, they're going to take that message. And they're going to take that as a science must not be really important. And finally, we need to engage students about their value commitments. This can get uncomfortable for us because I'm supposed to be this dispassionate professor at the front of the room, but we do need to engage the students. We need to find out, how does this science stuff you're learning fit into your worldview? How does this interact with the commitments you have, with the community you come from, with the career you're headed toward? How does this interact with that? And not just say, well, I gave them the information. It's their job to do something with it. Okay, so let's do a quick recap. So we talked about how learning attitudes operate basically independently of the conceptual learning. We talked about how assessing learning attitudes are complicated by response shift bias. We talked about how this 4-pass survey we came up with can highlight additional facets of student learning. We identified some trends that might help us understand student reasoning better, and we talked about the need to develop our students' attitudes as much as their knowledge. To my friends and former colleagues still on the faculty at Jacksonville University, I love you, I miss you, I'm praying for you. Thank you all so much. I'll take questions.
We usually have a microphone, but I don't have a microphone, so this is the microphone. So raise your hand, I'll come around with the imaginary microphone. If anybody has any questions?
So you mentioned this so you call it CLAS instead of class because it would be confusing if you call it class. That's not a good question. But, okay.
I heard one person pronounce it CLAS and they were from Colorado, so I assumed it was.
So I have a real question too. So the real question is, could you, since you kind of said that you just subbed in physics, chemistry, biology as buzzwords, can you just sub in the word mathematics instead, or do you have to change some?
So I don't know whether they've tried it. I do know that anytime we try to take something from science education, bring it over to math education, something doesn't translate well. And part of it is y'all are on a great parallel track with math education stuff. So there might be something similar in the math assessment world. If not, gosh, that would be a great project for an entire department to undertake and build and validate and publish. But I'm sure there's something similar out there, or at the very least, this gives you some idea of what to look out for in a sense. But yeah, it is interesting. Dear mutual friend Dan Mosley in y'all's math department, he tells me every time we talk, physics is 10 years ahead of everybody else in terms of educational initiatives. And that's someone else saying it, that's not me, so it's not egotistical. But it is kind of interesting because we come up with this stuff, we try to propagate it, and about 10 years later people say, wait, this is important, I should be doing this. So yeah, it's probably about time.
Get on.
Yeah.
Other questions?
Yeah.
You might have said it and I missed it, but what age or what year is this happening? Because I'm thinking about just the idea of maturity and personal development happening as well.
Okay, so I'm going to take that and in good seminar format, I'm going to tangentially answer something that's marginally related. So these were undergraduate students. Basically, we gave this survey to anybody who was willing to give it in their classes. And we had a wide range of university course numbers, but there's so fewer at the upper level that basically that data set is dominated by the freshman physics class, right? However, what's interesting, this is one of the papers that got me into the CLAS, that got me hooked into it, was if you give this survey to incoming physics majors, engineering majors, and everybody else, not to lump everybody, but just that's how the averages worked out. The general populace is at about the 50% mark in terms of expert-like attitudes. The engineering populace might be at like 55%. They might be marginally better. When you give this survey to a freshman physics major who just walked off the high school graduation stage and into your classroom, they score at the 90% level. Which means two things. First, it means whatever it is that triggers somebody to think like a physicist, it's happening before they set foot. And which used to frustrate me when we would have to go and advertise our majors to people. It's like, well, they've already decided if they want physics. I'm not going to convert anybody to a physics major. But the downside of that is that means we're not recruiting people who are different from us. Right? Because these attitudes, they're great, they're wonderful. They tend to promote the male and the pale. Right? And so if I'm going to get non-male, non-pale, I need to start engendering those attitudes, and I need to start investigating what other attitudes there are out there that might introduce somebody in physics.
So could I dive deeper on that? I'm an elementary school administrator.
Good for you.
The state curriculum
Yeah.
is garbage.
Yeah.
They have science once a week.
What?
Yeah. They have science once a week, but
Yeah.
every day they've got an hour and a half,
Yeah.
2 hours block of reading.
Yeah, so now, and you imagine this decline in expert-like attitudes. Most physics classes are not taught by physics graduates. Most physics classes are taught by chemistry majors, math majors, biology majors who go on loan to a physics class to teach it. And statistically, they don't have great attitudes toward the subject. So how are they going to instill any kind of confidence in our students or any kind of positive attitudes?
Maybe you should end on a positive note. What do you think?
Okay, so on a
what do you think is our best hope?
Okay.
I know changing attitudes, but that can be very
That can be done a lot of
very,
different
very
ways.
difficult
Yeah,
to
yeah.
do.
So, well, let me go back to that slide where we saw the ones that did work, right? Because this paper really kind of broke the narrative, because until this paper was published, we were all in the doldrums that this survey was unbreakable. And then they said, no, you can do this well. The thing to go to is this model building, right? And so basically, in a model building curriculum, what you're doing is you're not focused on the content. You're not focused on, I need my students to know F equals ma, W net equals delta E, and torque equals I alpha. You're not worried about that. Because if they're building models well, and if they're getting good data, they're going to learn that. But what you're focusing on is the process of treating them like a scientist while they're in the classroom. So instead of pointing and saying, look at all these great dead scientists on the wall, don't you want to be like them someday? It's, you can do science now when you can do it with this rinky-dink equipment that we have in front of you, and you can get excited about it. And when STEM was taking off, 5-10 years ago, and we got complaints from humanities that we were stealing all their majors, the thing I said was, look, the difference is that when a student comes into my physics class, I'm treating them like a fledgling physicist. I'm training them to be like me. When they come into your humanities class, you're having them go read dead authors, and they're never writing anything themselves. And so I think part of the hope we have is that once students get in, once they get into this sort of training program of what does it look like to be a scientist, what does it look like to be one of us, they can get very excited, even if they don't pursue that career, right? Because some of them are like, no, I am bound for industry, or I am bound for the medical examiner's office. And it's like, yeah, but I have this research experience. I have this experience of building my knowledge, of building a model, of working with the material, and that's something I can carry into it. I mean, we don't know what the world looks like if it's run by people who have that type of learning experience. We know what it looks like when it's run by people who have had the exact opposite experience, and they think science is just, some authoritative person telling you what to believe. And so I think there's hope there, but we need to make the case for that, and we need to show that, yes, this thing is working. So if I give a plug, we are in the process of doing that now with a couple of grants where we are training high school physics and chemistry teachers to incorporate quantum mechanical concepts into their classes.
Wow.
And so the reason we want to do that is because, number one, it's freaking awesome, and who doesn't want to learn quantum stuff, especially after Ant-Man came out and made everybody believe in the quantum realm. Ant-Man saved the physics world. But also because the day's coming when your average high school graduate is going to need a little bit of foundation in quantum the way they need a little bit of foundation in forces now. Right? Not that everybody's going to be solving the Schrodinger equation or validating the Heisenberg uncertainty principle, but just they need to know that there's this probability thing going on. It's weird and you can't get around it, but you can get cool devices out of it. Like there will come a day when they need that level of education coming out of your 11th grade physics class. So the way we're doing that, we're taking what's called the spins first approach, which focuses on electron spin that goes up and down as opposed to the mysterious wave function that turns everybody on. And we're doing that by incorporating some computational modeling into it that sort of helps them work with the math using a computer so they focus their brain cycles on the conceptual understanding. And we're hoping that model works. We're hoping it takes off, etc. If anybody's got a kid in high school physics or chemistry, go and bug their teacher to, come sign up because we've got a new cohort starting in the spring. But yeah, I'm hoping that type of stuff takes off and is able to help us.
Excellent. Any other questions?
I think it's awesome, like the idea of learning something that is absolutely valuable to you. And I think that's what like people get away from so much is like you are, even when you enter college, you are on a trajectory of learning these small scope of things, and the idea to bring physics or any type of science to people who aren't science majors is a pretty valuable endeavor in the long run. Whenever they tie that all together,
The thing I would love to do, whenever I am in a position where I design my own course again, the thing I would love to do would be take the very first week of the semester, we're not going to learn any physics. I want you students to go to your parents, some community leader you have, and some future employer you want to work for. And I want you to ask them, what should I learn in this physics class? And I want you to come back with that, and I want you to have some sort of outline of like 3 bullet points of here are the things that I think are important in my physics class. And then what I'm going to do is I'm going to find another student who's got a similar list. I'm going to put y'all in a group for the whole semester. And y'all are going to make, and the second week, y'all are going to make a proposal for a project you're going to present to us at the end of the semester. And you're going to make this proposal, and then you and I are going to sit down, and based on that proposal, I'm going to make a set of learning objectives for you, for your group. Now, there's only a finite number to choose from, so it ain't going to be that too hard of work. But then everybody's got their own individual learning objectives. And those objectives determine what they do in the class. So do you do assignment A, assignment B, assignment C? What combination do you do? And then, what's that?
It's a lot of work.
We have these wonderful things called computers. Because I can just go to a database and say, okay, this student needs objectives A, B, and F. So they're going to get these assignments. Boom, that's yours. It's yours now. It's what you wanted. And so if I can tie the curriculum to what the student wants, they'll be invested. They'll absolutely be invested. But I've got so many in my class, right? Because I've got them from all over campus and they're from all over the world. It's like, I don't know what you particularly are interested in, but I can take a week to find out and I can get you a plan for that. Anyway, pie in the sky dream. Hi, Abby.
Hi, I have a student question.
Please.
So you talk about integrating more attitude improving content into your actual curriculum. How do you combat college students' tendency to be kind of recalcitrant? Because I can't find a pattern to it. I would love to, but sometimes when a teacher or their peer says to them, you got to get excited about this, this is important in your life, this is fun. Sometimes they go, you know what, yeah, we can be excited about this. And sometimes they go, ugh, don't tell me what to do, teacher. So how do you combat that?
I think part of it is they have to find the excitement themselves. And so yes, I try to communicate my excitement, and I try to communicate that I am teaching you this because I think it's interesting to you, but I can't make them excited, right? I can't make them interested. But if I can give them an activity, and usually it has to be an activity in front of me, it can't be homework. But if I can give them an activity where they get to find something, and maybe it's a surprising thing, or maybe it's suddenly relevant, or whatever it is. When they say, "Oh, this is cool" on their own, that's the thing that I need. Now, again, the trick is finding the thing that's going to appeal to everybody, or giving a thing that is going to appeal to each person is tough.
Motivation.
Yeah. As an educator, you will spend the vast majority of your time motivating. You do not spend the vast majority of your time giving information. You spend most of your time trying to get them to be all excited. Today, I got students more excited in class just by telling them stand up and go sit next to someone you've never talked to before. And suddenly it became more of a norm that yes, I'm going to talk to my neighbor during this activity, and they were more talkative in class. And part of it is just their heart got pumping more. And so they were able to feel more. And sometimes it's just a matter of they need to not be sitting down at desks.
Yeah.
I've grouped students based on their favorite ice cream flavors, so you get a fun discussion for the first couple minutes about ice cream flavors,
Yeah.
and they're very talkative once you put them
Yeah.
in so people about
Let's thank
Thank
Dr.
you all.
Brandon. We are going on hiatus for December, so everybody have a lovely holiday. We will be back in the springs. We have talks that range from public health. We have a talk from a psychologist. And we also have a talk on turtles and much more. So please pay attention to our Facebook page. And I've been told by the younger hip crowd that we need an Instagram account. So that'll be coming. So look out for information from us. But thank you guys for coming out to Science on Tap. Thank you, Lemon Street, and thank you, Dr. Brian Lane.
So we just brought on Amber over there.
Thank you, Brian.
Oh, yeah. We're looking for a speaker for January. I think we have the other one.
I was like,
I was gonna say, I'll just meet you guys.
I switched my chair and then just kind of went.
yeah, I was like,
I'm telling you. I told her, I was like, you gotta like let them know.